Okay, it is Wednesday, November 11th. We're doing the review today for test 3, which is over chapters 9 through 11. Homework 11 is due tonight. We finished it actually Monday, so should be done with that and be able to get that uploaded tonight. Test 3 is going on today and Thursday over in the testing center, so make sure you get over there. And then we have chapter 12 starting on Friday. Now, first today we'll do a bunch of problems at the board here, working problems that combine reactions from chapters 9, 10, and 11. We'll do the alcohol reactions. Remember, we had dehydration, we had halogenation, we had some epoxide opening reactions, and then chapter 10, of course, we had the alkene reactions. And chapter 11 here, the alkyne reaction, those 5 key reactions carrying over. So we'll get to that in a second. Um, well, yeah, let's do those problems first, let's say, and then we'll go through the sample test. So let's start here with these problems, see what we've got. So here's a reaction. We've got what? We've got an alkene reacting first with HBr. So these are multi-step reactions that we'll look at first. And what does HBr do with the alkene? Well, it's going to form what? The more substituted bromide. Remember, by Markovnikov's rule, the hydrogen goes on the end to the less substituted carbon, or the carbon with more hydrogens. And then the bromide goes to the internal position, the nucleophile, because that's where more of the positive charge is, the more substitute carbocation. So this would be the intermediate here, the bromide, and then sodium acetate. What happens there? Well, then acetate can displace that and give the acetate ester product. So that's combining with what? Chapter 7 from before. So yes, we can use other reactions from other previous chapters in these sequential synthesis problems. But this one right here is what, from chapter 10, okay? So these synthesis problems can be a little more complicated than that. So sodium amide here, deprotonating the terminal alkyne. That'll form this anion here, which will displace here, okay? And that will put the propyl group here on the alkyne. And then 2 equivalents of bromine. That's going to add what? 4 bromides across the triple bond there. And we'll have the propyl there from the alkylation step. So this will give us the what? The tetrabromo alkane. Okay, so a 2-step reaction there. Acid-base chemistry here with alkylation. So that's again from a previous chapter, the SN2 reaction here on the primary chloride, and then bromination of an alkyne with excess bromine gives that. Okay, how about this one? Hydration of an alkene is first going to give us an alcohol, right? And that alcohol can be what? Deprotonated with sodium hydride. So after that next step there, you get that, which is an alkoxide we call. And that's a good nucleophile for what? To displace this bromide here. So you'll get an ether product. You'll get an ethyl isopropyl ether product there for that one. Okay, let's see. What other ones should we practice here? Oh, how about dehydration of an alcohol, followed by what? Halogenation. Let's take alcohol. Let me get these up here for you. I'm going to treat first with sulfuric acid. Then we're going to treat with chlorine and water. Then we're going to treat with sodium amide. So there's 3 steps. Sodium amide, NH2, sorry. And let's see, how about this one? Let's do an epoxide where we've got a couple stereo centers there. Let's treat first with sulfuric acid and methanol. And then what? Sodium hydride. And then isobutyl bromide. How about that? Let's see if we can do those two there. So if you want to pause your video, see if you can come up with those two products there. And let's see if you can do that. Okay, we're back. So what are we going to get here? If we do sulfuric acid alone, this first step, with an alcohol, right, we're going to get the alkene. So for these problems, no mechanisms required, but you should, remember the mechanism, especially for the fundamental reactions, and then know what the intermediate is. So we can isolate cyclohexene after this first step. And then chlorination with water will give us chloronium ion, top or bottom, and then water with loss of the proton out there will give us what? The halohydrin, the chlorohydrin. And then sodium hydride, you see, will form the alkoxide again. And now what can that do? Let's see, that's a good charged nucleophile. And look, you have a leaving group right next door. So let's go ahead and do what? The intramolecular SN2 type reaction. And we're going to get the epoxide, that's right. It doesn't matter whether it's down or up, right? It's achiral at that point. This intermediate's actually chiral, but it's DL, racemic, right? And so either enantiomer will lead to this product here, the epoxide. We'll learn another way to make epoxides directly from alkenes later, but this is the only way we know now from the halohydrin. All right, what about acid here in methanol? So that will give us what, an intermediate like this. And what, the methanol will form the methyl ether at that internal position. Yeah, so how does that go? Well, remember we protonate the epoxide and open it up this way under acidic conditions to give this carbocation. Now, there's no stereocenter there. That's flat. I guess we should have some stereochemistry here on the alcohol that results from that after it pops open. But the methanol can attack either the top or bottom, so you get a mixture here. It's not really too critical. It probably comes in mostly from the bottom, the trans there, but you should recognize that this is a free carbocation. It's going to give a mix, actually, of diastereomers, cis and trans. And both of them are chiral, they're both racemic, whatever. But now what's the next step? Sodium hydride. Yeah, we'll form this alkoxide again. And then that's a good nucleophile, right? Primary halide is dumped in a second step. We should have a slash there for step 2 here. And that'll give us what? That'll give us this diether, right? So there'll be a methyl ether there. And what? A isobutyl ether on that side. And yeah, if you show trans, it's probably the major one. But again, like we said, there's some ambiguities here with the tertiary cation. So does that look okay then? Yeah, okay. Let's go on to a couple more here. Multi-step synthesis here, which is involving multiple reactions. So these are harder problems, you could say, but we're showing you all the reagents. We'll do it in the opposite direction here. We'll show you the product we want, and then you got to provide the reagents. So there's a couple ways we can do these synthesis problems, right? Let's do another one here. Let's have this chiral alcohol, just one form. What is that? That's the S. Let's treat that first with tosyl chloride and pyridine. And then let's treat that with methyl sodium sulfide. Okay, so what's the product there? Let's take this same alcohol, treat it first with SOCl2. You should know the name of that reagent, thionyl chloride, pyridine. What does that do with alcohols? And then let's do the same thing, the same reagent here, the sodium methyl sulfide reagent. Let's take this primary alcohol, treat it first with PBr3, and then treat it with lithium acetylide, and then treat it with boron, borane, and then peroxide base. And yeah, see what we get there. So that's a 3-step one there. If you want to pause and work on that, fine. Okay, we're back. So what do we do the first step here? Well, we just form the tosylate. Okay, and hopefully that's in your screen there. Let me double check that. Yeah, that's showing up good. Okay. And notice we don't bother the stereocenter. It stays what? It's still S. Okay, verify that. In fact, the reactivity, if you want to think about the mechanism, it attacks the chlorosulfonate there. Remember, the tosyl stands for para-toluene sulfonyl chloride. You don't need to know that, but know what the reagent is and know what the reactivity is. This is not a leaving group, whereas if we tosylate it with retention of its stereochemistry, it becomes a great leaving group. And now we're in the presence of a great nucleophile, right? Sodium, assign your charges there. Sulfur is your nucleophile. Backside attack here will give us what? The inverted stereocenter right there. So the sulfur with the methyl group will be there, and that's indeed what the R product there. SN2 reaction. After we do this alcohol reaction from chapter 9 to convert it into a good leaving group. All right, let's do thionyl chloride pyridine with the same alcohol. What do we get now? We get the inverted chloride, okay? We're converting it into another good leaving group, right? But now this is what? The R chloride. It goes with inversion. It forms the sulfonyl chloride leaving group, and then there's a chloride byproduct here, which is nucleophilic enough to do the displacement directly, okay? So Socyl and phosphorus tribromide with chiral secondary alcohols will invert the stereocenter. And now what do we mean here? Oh, the same reagent, methyl sulfide, and that will give us, again, the methyl sulfide. But look, now the stereocenter is what? Back to S, I think, yeah. So we started out S, we stayed S with the tosylate, inverted to R. We did 2 inversions here due to the nature of those reactions. This one forms an in situ, we say, leaving group within the same reaction mixture. And then chloride can do the displacement to there. So this one inversion. And then a second inversion with the nucleophile, what? 2 inversions equals retention, you could say. Anyway, interesting comparison with complementary selectivity on the stereochemistry. All right, what about this one? 3 steps. PBr3 is going to do what? First form the primary bromide. And even though you have branching, PBr3 will not do rearrangements. It's a very good reagent to convert primary and secondary alcohols into bromides, okay, without rearrangements. And then we have the displacement here. We're going to form what? The acetylene. So we just formed this bond right here with the lithium acetylide, okay? That's a good nucleophile. Acetylides are fine with primary leaving groups. Secondary, tertiary with acetylene anions, they're too basic. They'll often do eliminations. But we get this terminal alkyne, and then what? We hydroborate it. And where's the boron going to go? Right, it's going to go on the end here. We're going to have a vinyl borane, and then we're going to oxidize that. Let's look at that oxidation intermediate. It'll look like that, right? Which is the enol form. That's an alcohol just after the hydroboration, right? We get that. And then what? With water here, and we'll get what? The aldehyde product, okay? Kind of count carbons there, make sure we got the right thing. So these 2 carbons here came in from the acetylene, right? And then the isobutyl group came in from the isobutyl bromide, we'd say, and that came from the alcohol. So look, we converted this alcohol we added 2 carbons to it, and we converted it into an aldehyde. So that's a very useful combination of reagents. We say alcohol to a leaving group, put 2 carbons on, and then regioselectively do the carbonyl formation. If we would have just used water and strong acid here, we would not getting the aldehyde. What product would we have gotten if this last step was sulfuric acid and water? Yeah, we would have gotten the ketone at this 2 position, okay? They both put in carbonyls via enols, but this one tautomerizes what? Because the electrophile in this case is boron electrophile on the end, hydride in the internal position, oxidation, then tautomerization to the product there. All right, let's do some more problems here. How about if we reverse it up? Let's do problems where we have the product and starting material shown, and then you've got to provide the reagents, how to get there. So let's start with this one. So there's a terminal alkyne, and whatever the steps we need here, and here's our final product we want. We want this geminal dichloride, okay? And how about this one? We'll start with a bromide, and we want to get this aldehyde. So, you know, some of these, you already know what type of reaction you're going to have to use here. You only know one sequence of reactions right now to form an aldehyde, right? Hydroboration of a terminal alkyne. So some of these really stand out, and you can move backwards for some of these. This one here, you got 1, 2, 3, 4 carbons, whereas you need 1, 2, 3, 4, 5, 6. A lot of these synthesis problems where you're not given the reagents map on to there from the desired product onto the starting material, and then try to figure out what reagents you might need. Often it's this next step back that will tell you what's going on. So you can kind of see, well, if we do hydrochlorination of an internal alkyne right here that we can get here, can we add on 2 more carbons for that alkyne? Yes, I think we can. Okay, how about this one? Let's start with that same terminal alkyne, and let's try to get this product, which will have, oh, the primary alcohol out here. Okay, so see if you can work on those 3 problems there. Pause the video if you'd like and see what you can come up with. Okay, we're back. So what do we need to do here? We've got 4 carbons. We need to have 2 more. So let's treat it first with sodium hydride or sodium amide. Make sure you show the base and show the reagent. Now, if we form that, we need to put on 2 more carbons. So how about an ethyl bromide? Okay, and you can show any reagents you need here. Sometimes we'll specify exactly what we need you to start with, but most of the time, these synthesis problems, starting with any reagents or any substrates you need, as long as you start with the given substrate that you're shown here. So after that step, what do we get? We get the alkyne with an ethyl, okay? Now, we know how to convert alkynes into dihalides, right? What reagent's that? Not chlorine, not Cl2. That would form the tetra chloride, right? What do we need here? We need excess, we'll say how many equivalents specifically of hydrogen chloride, HCl, okay? If we bubble this strong acid in here, we'll get the dichloride. Now you might say, well, which side will get the chlorides? Well, it's symmetric. There's 2 ethyls on either side. And remember, it's geminal, so after the first one, it's gonna look like this, chloride. And then the second equivalent, what? It's going to protonate out here to give the more substituted carbocation, and then the chloride nucleophile attacks where the chlorine already is, right? And so the second equivalent will go there. So yeah, you don't need to show that intermediate here. You just need to show 2 equivalents of this reagent going right to that. And usually these problems, you don't need the mechanism, but thinking about the mechanism often helps, right? So that can be useful there. Okay, how about this ethyl bromide to this aldehyde? Similar thing, we need what? 2 more carbons. And you only know one reaction forming that. So what is that? It's from this terminal alkyne that we can what? Hydroborate, borane, and then peroxide, and base. Okay, and that will give the enol right here, and tautomerization will give the aldehyde. So you already got part of it just thinking about the first step back retrosynthetically. And that's that open arrow when we think about synthetic planning. The retrosynthetic arrow is in the backwards direction. Sometimes that's helpful to think about that way. All right, so how do we go in the forward direction? How do we convert the ethyl bromide into that? Yeah, we need sodium amide or sodium hydride, doesn't matter which one. Nope. Well, we need to convert the reagent to that, which is this. We'll need the lithium salt. And you can just show the deprotonated thing. I was thinking about this, though. If we say starting with acetylene, then you'd have to show lithium amide or lithium hydride to form that reagent first. Then you add in the ethyl bromide, then you get that to make that bond right there. Okay, so either way, just try to be clear what you need there. But if it says any reagent, any reaction, you can just show the strong nucleophile, the charged acetylene anion nucleophile to go to there. But you need to show this intermediate. You need to show the reagents needed, and the product usually is given for you. All right, let's get a little room here. That one got a little too messy. How about this third one here, where we've got the butine, 1-butine, and we're going to this, hexine all for 1, 2, 3 hexine, 1 all. Yeah, 1, 2, 3, 4, 5, 6. You should know how to name those. The alcohol always has priority regardless of where it is on the parent, but how do you get there? Well, we've already mapped on to that, right? The 4 carbons there of the terminal alkyne. So what do we need to get to? Well, we need to take this proton off. Our intermediate would look like that, right? And then how do we put 2 carbons on? Well, we could have put, ethyl bromide or ethyl iodide or chloride, but we need an alcohol at that 1 position there. So what reagent are we going to show here? Right, epoxide. Epoxides are very useful for synthesis because they bring in 2 carbons and functional groups. So very useful that way. So this will pop open like this. Doesn't matter either side, it's symmetric. It will give us what? The 2 carbon guy and O minus there. And then what do we need to show here? For the second step, we need to show alcohol. So that needs to be over your arrows. So you need to show sodium hydride, then you need to show epoxide and water. You don't need to show the mechanistic part or even this intermediate. The water will take that and go directly to the desired product. Questions on that? Okay. Very good. Let's do a couple more, maybe. How about a bonus problem here? In fact, this is a reaction that we didn't cover here in chapter 11, but I think you can figure it out. Let's take bromine and water. I told you we didn't do halohydrin reaction, but you can figure this out. And this goes to this bromoketone product. So can you push electrons to convert this alkyne to this bromide? And, this is a new reaction for you, but I think following the principles, you can figure that out. So if you want to pause that, work on that, that's fine. So what would you get here? You'd get the same bromonium ion. Okay. And if we just attack with bromine and open this up, we'd get the dibromide. And if we had an excess of bromine, we'd get the tetrabromide, right? But what else can happen here? Well, water can interrupt things here, okay? So water can actually open up this bromonium ion. And what do we get? The mechanism, you'd have to show this. You'd have to show water on there, okay? And you'd have to show bromide or another water molecule taking off that, okay? And that will give us the enol, the bromoenol, right? That enol is kind of the key thing there. And then how do we get to this? We got to get another hydrogen on this carbon, and we've got to get a carbonyl there. So you can take water and kind of do the whole thing at once here. And you see that will go directly to the product here. You'll put that second hydrogen there. Yeah, sorry, you got to rotate the thing around. You see that forms your carbon-oxygen pi bond right there. And it just regenerates water. Water is just a proton donor and a proton acceptor. You just push the electrons around there. You don't need to use acid. You could use acid here. You're going to form some hydronium ion right there. You could protonate here, bring these electrons down, and then deprotonate there. So you could make that mechanism a little more complicated. I wanted to keep it straightforward. But for full credit on a problem like this, and this is a new reaction, but I think you can follow that. One thing people might be concerned with is, why did we attack that carbon? Well, more of the carbocation characters there, that's the internal position. But why did we show the cis, Well, yeah, we could have had the trans here if we did more of a backside. But actually, as this begins to open up, water can go on either side, and it doesn't matter. This isn't a stereocenter or anything. So if you showed either the cis or the trans enol intermediate, it would have been fine. The key thing is bromonium ion, using water as a nucleophile, deprotonating the hydronium ion, and then tautomerizing. That's the key thing there. The carbonyl, carbon-oxygen pi bond is always more stable than a carbon-carbon pi bond. But I think that's good. See if we got questions on that. I'm going to refer to some things there, but I think we're okay on that. All right, let's go to the computer here, and let me see. I think I need to refocus here. Sorry. Yeah, let's go down to the computer. Yeah, let me make that a little bigger. And this is a sample test, of course. You've got this on Learning Suite, so make sure you're looking at that and look at the problems there. Don't just work these problems, though. These problems won't be on our test, but similar ones to it will be. Always write a test to be comprehensive, to cover the topics, to have a combination of single concept type questions that are a little more straightforward, and always some harder problems that require you to bring together multiple concepts to do things a little bit differently. So what do you see here? Yeah, I think this first page is some nomenclature, some general ideas here, reactions of epoxides. Guarantee you there'll be some sort of epoxide reactions on our test. Under acidic conditions, the acid protonates the oxygen, and then it forms the more substitute carbocation. That's under acid conditions. So that's like with sulfuric acid water or some other nucleophile. We got tosylates. We just talked about that. Retention of stereochemistry. And know what the reagents are. We got thionyl chloride. We've got borane. We've got 9-BBN. What are some other reagents? Phosphorus tribromide, POCL, phosphorus oxytrichloride. So yeah, there are quite a few. And then you throw in the bases that we've learned before, sodium hydride, sodium amide, things like that. So yeah, I know it's a lot to keep straight there, but yeah, so this is thionyl chloride, SOCl2. Some of these don't have the right number of oxygens or whatever, and a carbon there. No, that's not it. And this doesn't even have the sulfur in it. So some things you can rule out there if you don't remember what thionyl chloride is, but you should know that reagent. We just covered it there. There'll be some properties questions. Soluble in water has to do with what? Hydrogen bond donor and acceptor that alcohols uniquely have. And what? A small nonpolar side here. And the primary ones are always more soluble. You got 3 primaries. Tertiary one, no. But it's only got 4 nonpolar carbons. This one has a lot more. It might be kind of difficult to determine which of these two is more water soluble, but here this one's primary ethanol and the small alkyl group. So examine all four of the questions. That's always a key on a test, right? Don't just jump onto one and say, oh, there's a primary alcohol. Well, examine the other ones carefully, and then make the best decision there. Let's see. Let's go on to the next page so you can see there. Carbocation undergo rearrangement. Yeah, that's the one with branching next door. That would do a hydride shift to go from secondary to tertiary. Primary alcohol, so that's just identifying things there. I don't think that's too bad. In fact, all of these I think are pretty straightforward. Yeah, the naming there. Let's just go on to page 3. Molecular orbitals, always an issue. And our new functional group here is alkenes. So this is what? The pi bond. This is the one that's occupied in the ground state. So that would be our highest occupied molecular orbital. This one up here is out of phase, right? There's a node right here as well. So that's an anti-bonding orbital. That's the pi star. That's what the star means there, an anti-bonding. So those two things together, the star there and anti, should lead you to that. Degrees of unsaturation, make sure you know how to do that. Let's see, select the best sequence. Oh, so here's a synthesis problem. Given the product here, it's a chlorohydrin. So you probably need an alkene right here. So how do you get an alkene from that? No, you don't want to form the bromohydrin right away. This combination of reagents is not for alcohols. So that's why understanding a second level of understanding in OChem is what? Reactivity. Specific substrates with specific reagents. This is a nonsense combination there. Chlorine and base with an alcohol. That's not right. It'll actually form a hypochlorite, but that's something we haven't learned. So this combination here is a no-go from the beginning. But POCL, phosphorus oxychloride and alcohol, yeah, we know that works. So at least this first part here. And yeah, that'll form cyclohexene. Okay, so that one might be a good one. Let's examine the others though. Socyl, thionyl chloride. Yeah, that'll form the chloride here. And then base will do what? It'll just eliminate the cyclohexene, not the chlorohydrin. Okay. And look, here's another nonsense combination: borane and peroxide with an alcohol. No, we use that with alkenes and then oxidize the borane to alcohols. Okay. So D is a no-go, A is a no-go. I think you can see that. This one doesn't lead to the product, C. This one does. So chlorine and water, that's what? Your halohydrin, your magic combination. Okay, that's one you need to know. That's one of the big 5H reactions here in chapter 10. So know that one there. Let's go on. Let's see. Oh, here's one. I may have mentioned this, or it may have been in the book. Calcium carbide. What is that? That's an actual mineral that's mined out of the earth. Calcium carbide. And what is that? It's calcium, which is in the second row. It's an alkyl earth metal, so it's calcium +2 cation. So where's the -2? Well, it's right here. It's the acetylene dianion. Okay. If you crush up calcium carbide mineral and treat it with acid, excess acid, guess what? It generates acetylene. It just protonates the two negatively charged acetylenes there. So you could kind of figure this out based on what we're telling you here and what the products are. Not methane, we'd have to highly reduce that and break a carbon-carbon bond. Not ethylene, okay? And not carbon dioxide. There's no oxygen involved here. Well, maybe on the sulfuric acid. But here, if you think about the structure and what calcium is, remember I said if a metal's there, it's always plus, and then what? The other thing bonded here must be the minus. And there's no other atoms here. It's just triple bond with a double anion. So that one is a little tricky, but you could figure it out. This is the old way that acetylene's made. We now make acetylene different ways via dehydrogenation reactions that are more efficient, so we don't have to mine the mineral and treat with strong acid that way. But that's a good one, I think. Tautomers also here, what are we involved? Enol keto isomerization relating to proton interchange. We just did one of those. So that's just knowing the term and what things mean there, I think. All right, let's see, these last two are, I think, okay. Let's go to the next page, if you will. And I'll go to the board and work some of these harder ones. But let's just kind of go through them here at first and see what we need to do. So here's a reaction sheet. Maybe this third one down is a little tricky, although we kind of did one like that. There's the mixture of methyl ethers. We did one very similar to this just now. So this is an epoxide under acidic conditions. You want to protonate, form hydronium ion, and then break it open, break the bond at the internal position that gives some more substitute carbocation. And that's where the methanol goes in, either top or bottom, giving a mixture here. If you just show one or the other or show a mix, I think we give you full credit. However, here we're showing a defined stereocenter right here, right? This is an S stereocenter right there. And when the hydronium ion opens up, it maintains a S stereocenter right there for the alcohol. Both of these are drawn as S. So make sure you draw that carefully, at least for this one. The methyl ether you could leave as undefined. This is a mixture of what? Not enantiomers. This is not a DL pair. This is the RS and the SS. So these are what? Diastereomers of each other. But we're showing them each one explicitly and labeling the groups here. So you don't need to go into that much detail to get full credit there, I don't think. Hopefully that's okay. Then we got hydroboration here. Remember that goes with syn addition there. Hydride at the internal position, boron at this position, less substituted, and then retention of stereochemistry here. This is a mixture of enantiomers. There's two trans stereoisomers here. Make sure you show the trans as the optimal one there. Let's go down to this problem at the bottom, and that's what? Hydroboration of the terminal alkyne. So it's going to put boron here. Oxidize is going to give you a vinyl enol. And that enol will tautomerize to what? Yeah, the aldehyde. So there it is. Don't show the ketone product here. Don't show any rearranged thing. There's no free carbocation at this spot, okay? These are known to go by avoiding a vinyl carbocation. A nucleophile will get on there, hydride in this case, and then that just tautomerizes to the aldehyde product. All right, how about the next page here? Let's see, oh, naming. Yeah, so naming here with alcohols, so always give the alcohol the lowest number. It has the highest priority. And here we have the names and the numbers embedded here. This is a nonene, ine, all. And so the numbers are correct there. And this is E. If you said trans here, you'd get full credit too. Here you don't have to say whether it's E or Z, it's in a medium-sized ring, so it's always this. Then the alcohol, then the next priority group is the alkene. So this is what? Cycloheptene 1-all. 2 here is the position of the alkene. Then everything else is just numbered around relative to that. Epoxides, we know how to name those. They're epoxy alkanes, but this is an epoxy alkane-all. The 1 position is the alcohol. 2-3 position is the epoxy. Okay, so you need that in the front. 2-3, you need 2 numbers for the epoxy, you see. And then 5-bromo, and then the stereocenters there. I think that's good. Yeah, we might have nomenclature. We might not, you know, not that big of a deal. Let's see. This next one on the sample test is the stereospecific halogenation of trans and cis 2-butene. And so here's trans or E, here's cis or Z. And let's see, the isomeric give different products. So we give you some hints here. So these harder write-on problems, make sure you read these things carefully upon chlorination. And we show you the chlorine, the reagent. We're nice there. Show the 2 products. What is the relationship between the 2? One is chiral, one is achiral. So what are the 2 products that come about here? Well, it's the same reagent, and it's just a 2 alkene. So at first you're thinking, oh, what do they mean, different products? Well, and what's the relationship? Well, it has to do with the stereochemistry, right? So if we form the chloronium ion here on the top or the bottom, and then do backside attack to open the chloronium ion, we get this trans product here, right? And you see that trans relationship here. You still see the methyls trans to each other. This was that YouTube video. We showed you the YouTube example of this, which goes through stepwise everything here. If we attack the chloride from the bottom on this side and pop it up, it's still trans. And then we recognize there's a center of symmetry here. And if we rotate around here, then we see the mirror plane relationship. So this is what? This is a meso. These are the same. These are just different orientations of the same molecule. It has stereochemistry, right? This is the R and this is the S, and they're reflections of each other, the symmetry on both sides. So it's meso, okay? Achiral. But this one, if it's cis, you see we have chloronium ion top or bottom, and then backside attack. We still see the trans relationship here between the two chlorides, and the cis relationship still borne out from the alkene geometry. But then if we rotate around here, you see this is the RR enantiomer. And if we open up on the other side, we get the SS enantiomer. These are indeed chiral, right? They're enantiomers of each other. So this is one that's chiral. It's a DL pair. This is another that's achiral, okay? They're both 2,3-dichlorobutanes, but different things. So this is a level of complexity here, combining the idea of enantiomers linked to the mechanism of the chlorination, the chloronium ion, and then the backside opening. Check out the YouTube video again and the discussion from class, I think just last time. Yeah, we went over that just last time there. Let's see what else. The next page. Oh, this synthesis problem. So supplying the reagents there. I think those are pretty straightforward. Most of those, we've done some similar ones. Yeah, there's the epoxide. There's the phosphorus oxychloride forming the double bond right there. So POCL does the elimination. Or sulfuric acid, either one of these reagents would put the alkene right there, trisubstitute alkene. And then what? Hydrating the alkene, okay, gives the internal alcohol. Don't hydroborate there. That would give the primary alcohol, right? And we got POCL. I guess that should be with pyridine there, but yeah, if you just show POCL, it does the elimination of alcohol, especially secondary. It's actually limited to secondary. The book doesn't point that out, but the ones I'll have you use are secondary because those are the ones I know it works for, without rearrangements in this case. Then we got that alkyne nucleophile, and then what? Hydration of the alkyne. Yeah, it gives the ketone product. Okay. And then this one here, hydroboration, will give the primary alcohol. Okay. And then take that alcohol, deprotonate it, and then use that as a nucleophile to do what? The displacement of ethyl bromide to give you this ethyl pentyl ether product. Yeah. Oh, then we got problem 5 here, right? We've got a little bit trickier one here, which is a cyclobutane with an alcohol, 2 alcohols, right? A diol. And we show you the products, A, B, and C. Oh, we give you 3 products. And your challenge here is to account for all of these products. Now, this is a reaction that we haven't covered, forming ethers this way, or bromo alcohols, or an alkene alcohol. But we have covered what? HBr with alcohols. That's your typical what? Hydrobromination reaction of alcohols. Why are we reacting the secondary one first? Well, because that will give a secondary carbocation, okay? We don't want to form a primary carbocation. We are protonating this, it's reversible. The protons are going on both of these alcohols. But when the secondary one gets protonated, it forms the secondary carbocation. And now a shift can occur, right? To go to the strain-free secondary carbocation. It's still a secondary carbocation. Why did it shift? To relieve this angle strain. So you don't need to discuss all the issues here. You just have to come up with a reasonable electron pushing route to account for the products. So if we do a hydride shift here, so it's an alkyl shift followed by a hydride shift, tertiary alcohol Now our primary alcohol can come back and attack here. This gives you what? The six-membered ring ether here. We need to deprotonate there. That's A, right? Or if we attack with bromide there, so it gives a mix of products. I'm not sure what the ratios are. That's not really uh, material to this problem. The problem is, can you push electrons reasonably, come up with the right product? So this tertiary carbocation, same thing there. So we say, or, yeah, redraw it again so the grader can see it there if you're doing multiple things from it. And yeah, the electron pushing is important here. So that's the tertiary bromide there. And what was the last one? Oh, if we do a dehydration right there. That gives a tri-substitute alkene, that's stable. And yeah, that's C. There's a lot of that product too. So don't be too discouraged by these type of problems. Usually what you're going to do first is just something you already know. And then start to examine intermediates and think about, well, how can I get that to these products? That's the challenge for these problems. Obviously, it's a multiple concept question, right? With new and unusual looking products that you can see how these map onto the starting material. You can count carbons. All the carbons are still there, but obviously the ring has changed, right? It's a 5 and a 6-membered ring, 5-member ring. So yeah, you had to think about a ring opening thing there, okay? So, start trying it, use enough of your scratch paper, put the best answer down there on the space provided, okay? Use your scratch paper and go over it carefully there. That's usually the best approach to that. Let's see, what else have we got? Oh, we got these worksheet problems. They're, again, a collection of harder problems. They're similar to the challenging problems at the end of the chapter. So, work through these and see how some of these are. So it's just reaction problems, I think. Here's a challenging mechanism problem that involves first formation of the sulfur nucleophile, backside opening of the epoxide, gives the six-membered thyrane ring. Don't worry about the name of thyranes, but you can see that's where the nucleophile was. And you see the stereochemistry there is trans now. That's because of the ring opening backside attack. SN2, right? Okay, and then the O minus, which is generated, does an SN2 right there to form the 5-member ether here, okay? So, and then the variation here is just what? Oh, if you have ethoxide, which you do, primary bromide's a very good leaving group, and you get some of that there, along with the opening of the epoxide there. This is the minor product, you're told, okay? But the sulfide acts as a nucleophile in both cases. You still see the trans relationship there. So that's not too bad. Then we have an epoxide alkene reaction, opening up the epoxide in the right way. The alkene is a nucleophile, and we've seen this over and over. Alkenes in the 5 reactions are nucleophiles, right? This is just a different electrophile, okay? Same type of nucleophile. Tertiary carbocation again, and then deprotonation. Make sure you show that clearly. Chapter 10, harder problems. What have we got there? Some more naming. I like this one here, this name. So this is a 4 nonenal, okay? Even though you might say, well, the 2 bromides here could be 2,2, but then you'd have to have the alcohol with a higher number. So you always number down the parent chain to give the alcohol the lowest possible number because it has the highest priority. So yeah, sorry about that. Then we got some problems here, similar to ones we've been talking about, hydroboration. Here's one with a shift, yeah, after you protonate. Giving this shifted product. Mixed halides are also known here. It'll form the anion of the more electronegative one, and then it's a tertiary iodonium ion, which can open up to give the tertiary carbocation. And yeah, there is some chloride adding at the primary position, but it's not a great nucleophile, okay? So if it can ionize the tertiary carbocation, and you're showing the product there. So you have to say something about why this is the anion in your mechanism. I think this harder problem here was similar to a homework problem. So you've seen that iodo-lactonization, it's called, forming a cyclic ester, which is called a lactone. same iodonium ion, and then base. Make sure you show the carboxylate as a negatively charged nucleophile, better nucleophile. In fact, you got base there, you got carbonate, which can take the proton off, right? So there's two things going on here. Iodonium, cation, make sure you show a cation on your halonium three-membered rings, and then opening it up, you see the trans relationship there. Students often ask, well, why is the iodonium forming on the top? Well, it's trans to where the stereocenter is here. It's actually forming top and bottom, but then the ring opening thing happens better here to give the cis stereochemistry right there. So some reactions we've been talking about are actually reversible, protonations and things like that. Even halonium ions can be reversible, and you get the more reactive intermediate there. Let's see, just real brief. I wanted to go to the board and work a couple problems, but let's see, we may be running out of time. More nomenclature, more problems there for chapter 11, I think. Yeah, and that's fine. We've got some mechanisms. You got to push electrons for that. Multi-step ones. No, multi-step ones, yeah, we're just showing yeah, how we're hydrating, doing the hydration of the alkyne in the presence of an alkene. That one is, last step's kind of messy and won't be too high yielding, but the internal ketone is where you're going to form that. I think that's one where people might have some questions on that. But yeah, that actually works to convert this epoxide into this vinyl ketone. Enols, this idea of tautomerization combined with deuterium. What's deuterium? It's a heavy isotope of hydrogen. So this is heavy water or D2O. And you can see if we do the enolization here to go the enol form, that's a minor form. But then if we deuterate with heavy water and go back, here we can introduce a deuterium at the beta position. And we can keep doing that, right? Eventually we get deuteriums all over the place at the alpha position. We don't get deuterium down here or here because we can't go through the enol there, okay? But this is a reversible thing. Keto version here versus enol. In water, especially with acids, some amount of the enol will be formed, and then that can be equilibrated out, right? So you got excess deuterium here, and you only start with hydrogens in the substrate. So the heavier isotope can eventually, by equilibrium, take all the spots there. So that's a little problem that goes a little bit beyond a lot of acid-base chemistry or this concerted enolization, tautomerization thing that I showed you there. So let's see. Yeah, we're kind of out of time. Let's see, which one did I want to show? Though, well, I think we've covered most of them, very related ones on the board and in homework assignments. So I think we're okay. Work the files here that don't have the answers on them. So you have both files for the sample test, right? You have the blank one without the answers. Work that one first, and then look at the answers there. So that's another good strategy for working it. And work as many of the problems as you can. Keep up on your homework book challenge. Remember, that's still going on. If you can show me at the end of the semester your solutions in a neat workbook for all of the rest of the even problems at the end of each chapter, you'll get that grade boost if you're found to be in a borderline grade region. It's usually worth up to 3 to 5 raw points at the end of the semester, so it's not much. But when I do the grades, I'll look for regions where there aren't many scores. But if you're in one of those gap spots and you haven't done your homework book challenge, that can be detrimental to your grade then. And it's also a great way to get you to work as many problems as you can to get ready for this test. So I think we're good there. Went through the sample test and pointed out a number of things. We will see you next time. Yeah, I went a little bit over. Sorry about that. We'll see you on Friday. Very good.